This is an Atwood machine free response problem. Let's read the problem. Two blocks are connected by a string of negligible mass that passes over massless pulleys that turn with negligible friction, as shown in the figure above. The mass M2 of block 2 is greater than mass M1 of block 1. The blocks are released from rest. Part A says, the dots below represent the two blocks. Draw free body diagrams showing and labeling the forces exerted on each block. Draw the relative lengths of all vectors to reflect the relative magnitudes of all the forces. So part A is essentially asking us to draw free body diagrams of the two blocks. So we'll start by this will be the center of mass for block 1, and then over here, block 2. Now we can see from the picture that both blocks are held up by the same length of string attaching to the pulley. So this length is same as this length. So from that observation, we can determine that the force of tension on both blocks is the same. So we'll indicate that by drawing two arrows of the same length to indicate equal forces of tension. Now we are going to label the force of gravity on each block, which will not be equal, because if you look at the equation for force of gravity equals mass times acceleration due to gravity. Acceleration due to gravity is negative 9.81 meters per second squared, which means that g is a constant value, and whenever mass increases, the force of gravity will increase. As you can see, block 2 has a greater mass than block 1. So by that, we can see that the force of gravity on block 2 will be greater than the force of gravity on block 1. So we'll indicate that by drawing a longer arrow on block 2 than block 1 for force of gravity. And that is part A finished. Let's go into part B. Part B says, derive the magnitude of the acceleration of block 2. Express your answer in terms of mass 1, mass 2, and g. So, to solve this problem, it's asking for acceleration of block 2. So, what we need to do is use Newton's second law, which states that in a system, the net force will always equals mass times acceleration. Now, if you look at this system, for block 1, the net force would be force tension minus force gravity, correct? And we'll just call force tension T for simplicity's sake. So this will be T minus Fg, or also, as we found here, equals mg. So we'll just say mg. This right here is net force. This equals ma from the equation above. We'll just label this m1 for mass of the first block. And then we just do the same thing for the second block. The tension is equal, so we'll use T again. And then we'll use, I'll put the 1 here. Now you have mass 2 times acceleration due to gravity, and then mass 2 times acceleration. So we just used Newton's second law and plugged in the variables from both blocks. So now we have two equations, and they both have the variable t in it. So we can substitute t to get one big equation. So we'll manipulate this equation to get t equals mass times 1, mass of the first block times acceleration, plus mass the first block times gravity, for acceleration due to gravity. This is equal to t. So we plug that into this equation, so we get m1a plus m1g equals, oh sorry, no. m2g equals m2a. And we want to get both g's on the same side and both a's on the same side, so we bring that down here to get m1a minus m2a equals m2g minus m1g. Factor out the a over here, we get m1 minus m2. You can factor out the g over here, m2 minus m1. This should be. Oh, I made a mistake. For this equation, mass times gravity will actually be greater than the force of tension. As you can see in this force diagram above. Because this is the block that is causing movement in the system. So we'll actually have to flip these around so this answer won't be negative. So then this translates to, so instead of this, you would plug in t this here into this equation. We get m2a m2g plus, sorry, m2g minus m1g, m1a plus m2. You know, I'm just going to write on the other side here. So, alright, upside this time. m2g minus m1g equals m1a plus m2a. Okay. Now we can factor out the g's and the a's to get this equation. I'm trying to find acceleration, so we divide both sides by parentheses mass 1 plus mass 2. So we get final answer for acceleration due to gravity times mass 2 times mass minus mass 1 over mass 1 plus mass 2. And that is part B. Okay, let's move on to part C. Part C. Now there is block 3 of mass m3 is added to the system as shown below. There is no friction between block 3 and the table. Indicate whether the magnitude of the acceleration of block 2 is now larger, smaller, or the same as in the original 2-block system. Explain how you arrived at your answer. So now the Atwood machine is altered. They have added a block on top of the table, on top of the string, essentially. It's asking us to determine whether the acceleration of block 2 is increased or decreased or stay the same. So, we can say that since, originally, mass of the system was equal to mass 1 of the block plus mass 2 because the string had negligible mass. But now, they've added this new block, so the mass of the system becomes mass 1 plus mass 2 plus mass 3. So obviously the mass of the system increased. And we can also apply this mass of the system into Newton's second law. Net force equals mass times acceleration, or net force of the system equals mass of the system times acceleration. And we know that net force of the system will stay the same because we know that net force of the system stays the same because putting a mass in between the two blocks will not affect total net force, because the tension of holding up this block and tension of holding up this block will still be the same even if there's a mass here, and obviously the force of gravity will still be different, so it will still be the same as before, essentially. So the net force of the system will still be the same, but mass will increase. So obviously, because it's a is it indirect or direct relationship? One of those two. The mass will increase, therefore the acceleration will decrease. So by that understanding, acceleration of block 2 M2 is now smaller. And that is the entire problem.